And all credit to Michael Faraday for finding this cool little thing out. What he found out was this: when he was doing experiments in his lab, he found out that if the magnetic field of a circuit changes, an EMF is induced in it. Simple. So if you have a coil here, just place it here. The magnetic field associated with it is not changing because the Earth's field is passing through it, right? And it's not changing. The Earth's field is not fluctuating. But if you take a bar magnet and just throw it through the coil, through the loop or through the coil, as the magnet is passing through, the magnetic flux of the bar magnet gets linked with the coil. And then, so that means, if you look at it in slow motion, the magnetic field of the coil increases as the bar magnet approaches, and then as the bar magnet leaves, the magnetic flux drops. So there is a momentary change in magnetic flux associated with the coil, right? So whenever the magnetic flux of a loop, of a circuit, of a coil, whatever, changes, the word changes is very important, then an EMF is induced in it. An EMF is a voltage. And for the first time in history, a voltage was produced without using a cell, without using a battery. See, there's no battery there. And you get a voltage, you get a current, just by changing the magnetic field connected with that coil. And that process is called electromagnetic induction. So, electromagnetic induction is what you see there. The magnetic flux through a loop. Oh, sorry. That was slide number 2. So that's the definition of electromagnetic induction, and that is what this whole chapter is built on. A changing magnetic field or magnetic flux induces EMF in a circuit. As simple as that. And I want to tell you that this word changing is so important there. Because if you take a strong magnet, maybe the world's most powerful magnet, and keep it right there at the center of that loop, what's the induced EMF? Just, let's say this is the strongest magnet that you can find, and you take it and keep it at the center of a loop. Is the magnetic flux of the loop changing? You will not get any induced EMF. But what if you start shaking it? Well, then you see an induced EMF. If you go to the right, the induced voltage will be in a certain direction. If you go to the left, the induced voltage will be in the opposite direction. Okay. See, that's an iron core, a battery, a switch, and you have a galvanometer. You know that this is a very sensitive device. That means even a small current and it will give you a deflection. The question is this. You see two circuits, one on the left side, we can call that the primary, this is the secondary. Are they electrically connected? No, they are not electrically connected because this is insulating wire. Okay? Although this is iron, it's insulated, so the current doesn't flow through the iron. I hope you got that. So there is no source of voltage in this circuit. No source, no battery, nothing, right? This is just a measuring instrument. But there is a source on the left circuit. Now, when you close the switch, what was the current? Before you close the switch, what is the current in the circuit? 0. And when you close the switch, the current is going to grow from 0 to whatever. Depends on the resistance. Let's say it grows to 5 amps. Now, I want you to concentrate on the fact that the current does not jump from 0 to 5. It actually grows. Can you see that in slow motion? Like it goes from 0 to 1, 2, 3, 4, 5. And now, during that process of growth, the magnetic field that the current is producing is also changing. Because in the last chapter we saw that every current produces a magnetic field, and the strength of the magnetic field depends on the strength of the current. You got that? So when you switch on that switch, for a moment, maybe in 1 second, the current increases, and during that time, the magnetic flux changes. And because this is a ferromagnetic material, it takes that changing magnetic field and connects it with the secondary circuit. So now to say the secondary circuit is feeling a changing magnetic field. And therefore you will see that just when you close the switch, the galvanometer will give a momentary deflection, showing that a current was induced in this coil. Now the same thing happens when you switch off. When you switch off, what's going to happen is the current drops or decays from a maximum to zero, the magnetic flux drops, and therefore another induced EMF is produced here, which will be in the opposite direction. So if this had been to the right, when the current was growing, it's going to be to the left when the current decays. You got that? Now, if we could just have a mechanism where you could have it switch on and off continuously, don't you think that you would get a continuous current in the other circuit? That's where we're coming to in a generator. Well, we're not mechanically switching on and off, but there's going to be a process where that happens, okay? So that is electromagnetic induction. This formula actually gives you phi or phi B is the magnetic flux. B stands for magnetic. Magnetic flux is given by B perpendicular A. That makes sense? Which is B dot A. And how do you define B dot A? BA cos theta. BA cos theta. When theta is 0, causes, okay, that makes sense, because now it's 0. Cos 0, maximum flux is passing through it, right? Okay, so now if you continue, you can write this as BA cos theta, as I told you. That particular figure brings more sense into it, if you try to understand. You see the angle between the magnetic field and the area, that's taken to be the direction of the area. And theta is the angle between them, and so on and so forth. So that's how you get it, BA cos theta. Okay? Now the most important law of electromagnetic induction, there are actually two laws. One is Faraday's law, the other is called Lenz's law. Faraday's law and Lenz's law. According to Faraday's law, the induced EMF is equal to d phi by dt, rate of change of magnetic flux. Induced EMF is equal to the rate of change of magnetic flux. That's for one loop. So if you have n loops, you just got to multiply that with n. So you will get E is equal to minus n d phi b by dt. All right, I'm going to explain that and then go to the direction. I've got to explain the negative. Okay, but just try to understand this. What is d phi b by dt? The rate of change of magnetic flux. So let's say that you rotate this slowly. You are changing the magnetic flux by changing it slowly. So the induced voltage would be small. But if you rotate it fast, it's the same change in magnetic flux, but you're changing it faster, so you get a bigger voltage. Does that make sense? I don't know, here on bicycles, we do not use generators, but have you ever seen a bicycle powered by a little generator that connects to the rear wheel of the bicycle? When the guy pedals, there's something touching against and rotating. It's actually a magnet rotating inside a coil, that's all. You have a magnet like that rotating inside a coil. And it's connected to a bulb right on the handle. So the idea is that when this guy stops pedaling, there's no light, because there's no rate of change in magnetism. But when he pedals faster, the bulb becomes brighter. That makes sense? That is Faraday's law. So according to Faraday's law, finally, according to Faraday's law, the induced voltage or EMF depends on the rate of change of magnetic flux and also depends on the number of loops. So, to do problems, understand, this is the rate of change of magnetic flux of one loop. d phi b by dt is the rate of change of magnetic flux of one loop. That's why we multiplied it with n to give you the total voltage. Now, to get the direction, you have to go to Lenz's law. This is crazy. Lenz's law tells you that, let me have your total concentration here, because there's going to be, otherwise, real confusion. When the induced current is produced, well, the induced EMF is actually giving rise to an induced current, right? You with me? Okay. Every current has a magnetic field, isn't it? Come on. Wherever there's a current, there's a magnetic field. Now, the induced current will give rise to a magnetic field, which will oppose the change in magnetic field that produced it in the first place. I'm trying to say that again. Why was the induced current produced? Because a certain magnetic flux changed, correct? Maybe, let's say that it decreased, because a change could either be decrease or increase, okay? Slow down. So, let's say a magnetic flux decreased, and that gives rise to a current in the circuit. Now, that current produces a magnetic field, which will try to stop the decrease in the magnetic field that produced it. I hope somebody got it. That explains the negative.
One more time.
That explains the negative. One more time in another way. It's like a son opposing a dad. For sake, because I don't get a better example. You oppose the one that produced you. You oppose the one that produced you, like a son opposing a dad. What produced the current is the changing magnetic field, isn't it? And when the current is produced, it gives rise to a magnetic field that tries to go against. If it was a collapsing field, this current tries to maintain that field. I'm not saying that it will succeed completely, but I'm trying to say that at least it will slow down the rate of collapsing of the field. Are you with me? But if that was a field that was increasing, then what does this induced current do? It produces a magnetic field that tries to reduce it. That's it. That explains the negative sign. So the induced EMF is always opposite to the rate of change of magnetic flux. That's what that is Lenz's law. Okay, that is tough, but I'll make it easy with another example that you should get. The direction of the induced EMF is such as to oppose the cause that produces it. That is Lenz's law. To oppose the cause or the change in flux that produces it. Whatever caused it, it opposes it. That is Lenz's law. Number one, a changing magnetic field. How? There are three ways, and we've talked about this. A changing magnetic field may be like this, dropping a magnet. Number two, by changing the orientation of the coil. You remember where we talked about rotating a coil? How it is situated. By changing the orientation of the loop in the field. Or number three, by changing the area of a loop. That is going to be really interesting. All right, look at this diagram, and you know what I'm talking about. This is number three, because we talked about 1 and 2 before. All right, what do the crosses show? What kind of magnetic field is this? Into the paper. That's a magnetic field into the paper, and you have a certain loop, a flexible loop there, and it has a particular area now, and what happens now is you just stretch it. You didn't even rotate it, you just stretch it, and doesn't the area change? Of course it changes. And if you just keep doing that, you will get an induced EMF, because you're changing the area. So you can either rotate it, keeping its area constant, physically rotate it, or keep it in the same direction, like you're not rotating, but you're changing the area. So you can produce it in three ways. In fact, when an airplane flies, let's say it's flying horizontally, there's a continuous induced EMF. Can you tell me why? Okay, that's EMF induced in a moving straight conductor. The figure explains it clearly. Okay, let's watch and get this in the next 5 minutes. What kind of field is this? It's out of the plane of the cable. And you have a kind of loop like that with a movable part. You know, it's kept horizontal like that, so you have a movable part which you can move. You have a wire bend like that, and then a movable part, so that the circuit is always completed. That's what I mean. So, and you move it through this magnetic field. Isn't the area changing? The enclosed area? Come on, the area of the loop is changing, isn't it? If the area of the loop changes, surely there's going to be an induced EMF. We're going to calculate it. Faraday's law, E is equal to what? d phi by dt, d phi b by dt, and I've not put the negative there. Maybe I'll remember and put it. Okay, and when you remember phi b is b dA, why? Because B is constant. Isn't it a constant magnetic field? So B is constant and it's area that's changing. So when you take that, you get B dA by dt. And dA, isn't this the change in area in this figure? Watch. Isn't this the change in area? Isn't that length multiplied by B dt? Come on. Where B is the velocity with which you're moving it. Because this is the width. So that's why it's length multiplied by B dt divided by dt. The dt's get cancelled and you get a cool formula there. So the induced EMF is B times the length times the velocity.
It's not negative?
But you could put a negative, but remember that the negative only shows the direction. It doesn't affect the magnitude. So if you don't put a negative. Okay, and I have to tell you that this is not a general formula. This is only true. Okay, somebody tell me what theta is here. 90. This is only true when it's 90. Otherwise, it will be BLV. Now is the point.
No, it's 9.
Why?
Well, it's 90, it's more.
Okay, so it will be BLV sine theta generally. Theta is 90, sine 90 is 1. So now you understand that if the velocity is really high and the length is also high for an airplane, tip to tip is really huge, you could get a big voltage. Okay. Now the generator, finally. I've already given you the principle of a generator. That's the construction. You have a coil. That's a coil. It's called the armature, rotating between the poles of the magnet. So that's a magnetic field from north to south, you know that, and that's a coil. And when it rotates, there's a continuous change in magnetic flux, and so you're going to get, we talked about this, a continuous voltage here. These are called slip rings, and it's a physical arrangement to enable this part to rotate without entangling the wires, of course. It's normally made of carbon and you have carbon brushes brushing against it, and because of friction after some time they have to be changed. That's why generators have to be shut down once in a while, you know, for the process and all that. Anyway, well, what we need here is a formula. An equation using Faraday's law. Remember, the only formula that we have studied so far is Faraday's law, which is E is equal to minus d phi b by dt. The negative is because of Lenz's law. In this case, it's going to be BA. We're talking about one loop, BA cos theta. And I just want to ask you, what's theta? In relation to angular velocity omega, if you remember that. Omega is defined as theta by t. So theta would be omega multiplied by t. Angle through which it turns, that's from semester 1. Theta is omega t, so put that back there and differentiate. When you differentiate, you take out the constants. B and A are constants. Correct? The only thing that changes is the angle. And therefore, and what's the differential of cos? Negative sign. So you have negative sine omega t. And do you remember that you have to take omega once more out because it's a constant? You're rotating it at a constant angular velocity. And you end up with two negatives, making it a positive. And you get BA omega sine omega t. That's for one coil, one loop. If it has n loops, you just multiply this with the number. And you get the final formula, NBA omega sine omega t. And all of these are constants. So we can put that as E naught. So remember that E naught is NBA omega. So you get E is E naught sine omega t. Let's discuss that for some time. So can you see that the induced EMF is not constant? At least can you see that it's not a constant? Oh, well, it changes with t. It's going to be a sinusoidal curve. It's going to be a sine curve. Does anybody know how a sine curve looks like? Up and down. Like a wave, isn't it? That's what is called an alternating EMF. So that's an alternating generator. Does it flow in one direction? No. Because it has two halves, the positive half shows that it's flowing in one direction. The negative shows it's flowing in the opposite. Now that's the type of current that we use at home and in school, as compared to the current produced by a battery. Compare the two. A battery produces a current which has a constant direction, always from positive to negative. You see that? Unless you flip the battery, which you don't now. But here, and remember that its magnitude is also constant. That is a direct current. See, now that's why it's called a direct current, because it flows directly in one direction. One direction. Constant magnitude, unless the battery dies. You know what I mean? Here, both the magnitude and direction are changing. Did you notice that? How is the magnitude changing? I hope I have a figure for this. If not, I'll have to draw it. Okay. I hope it doesn't go over something. I don't care if it does, but this is the type of EMF that you're going to get. You see this? And what you have on the x-axis is time, and what you have on the y-axis is the EMF. So is the magnitude changing? So what's the magnitude here? How much? Go back to that equation. When theta is 0, sine 0 is 0. And here what's the angle? 90 degrees, pi by 2 radians, because sine 90 is 1. And then what do you have? What you have is the maximum. That's the maximum. Are you with me? Sine 180 goes back to 0. Sine 270, negative E naught. Sine 360, which is 2 pi radians, is again 0. So you see that the magnitude is changing from 0 to maximum to 0. In one direction, and then suddenly it flips over. This is crazy. It flips over, opposite direction, and changes. I hope you enjoy what an alternating current is. And there was a big fight going on between two scientists. Go Google it and find out who are the two scientists involved. If you know it, don't give it out. That's the word for today. That could have changed our generation forever. One said, we need to have DC going over the lines. Another said, no, it's absolutely not DC, we need to use AC. And it was a battle of not only words, a battle of ideas, went on for some time, and I'm happy, and both are very popular scientists. Send it to me today. Whatever you get from Google, send it to me, I'll give you some extra credit. Who are the two scientists? And one of them won, of course, the one who said that we should have AC going all over the cables, not DC, ultimately won. He didn't have many people with him. Please don't Google now.
I'm still looking forward to like this.
So go over that. So this is AC. And we'll see that there are so many conveniences of sending AC rather than DC. We're coming to that. Because you can never use a transformer on DC. Did you know that? Transformers will not work on DC. Transformers only work on AC. And then now you've got to latch on to the idea of, I'm trying to put some life into this. Why do we need a transformer? Why do we need a transformer? Let me spill the beans and give you the idea. Remember, when a current flows, heat is produced, isn't it? And the heat produced is given by the formula I squared R, if you remember. So the heat produced depends on the current. So if you could propagate a very low current over these cables, a small current, then you made sure that the heat loss is reduced. Make sense? For which you will have to step up the voltage. Because in a transformer, when the voltage goes up, the current goes down. You got that? So a step-up transformer is where the voltage is increased, but at the same time the current is decreased. So at the generating station, wherever it's generated, they have a huge step-up transformer. Before transmitting the AC, they step up the voltage. That's why you see 11 million volts written there, danger. The voltage is really high on these transmission lines, but the current is small. They did it on purpose so that the heat produced or heat loss is reduced. You get that? But before we can use it in our homes, we need to step down the voltage because we only need 120 volts. But we need a bigger current. We need at least 15 ampere in our homes. So that's why you have substations. In a substation, you have a step-down transformer where the voltage goes down, but at the same time, what happens to the current? Comes up, and then it's taken to our homes. And you know that in our yards, in the homes also, you have step-down transformers to stabilize the voltage so that it's always 120 volts. We'll get to this later, but I was just giving you, what do you call it, a sneak peek into transformer and all that stuff that's coming. So now all the theoretical stuff that we studied has suddenly become practical. You see that? All the magnetism and all that, we had to have this to get this. Okay. What I'll go and do is, I'll clean this off because I don't know what's coming. Let's see. Oh, is that a problem now? Can't remember what I... Okay, I think it's problems. So let's, because I knew I had to break it somehow, because I can't give you the whole theory, right? The concentration gaps. So let's do 5 questions in 5 minutes.
5 questions, 5 minutes.
Woo! I will be good. You'll see how easy it is if you follow me along. And then some kind of difference. Then go back to the theory. But I forgot to record this, so anyway. 0.053, and the unit would be, it would be positive because there are 2 negatives. Remember there's a negative here, and then there's a negative here, which I forgot, right? So it will be positive, right? Because the formula has a negative and d phi b is negative. So, but do not worry too much about the negative thing. Normally the magnitude that you're interested in. So, all right. Because it says that the field is pointing into the paper, isn't it? And see, what's the A part? What's the A part of the question? Come on. It says, what is the direction of the induced current? That's what I just answered. What was the original direction of the magnetic field? Into the paper. And what's happening to the area? Is it increasing or decreasing? Decreasing. Decreasing. That means the magnetic flux is changing. Decreasing, I mean. The magnetic flux is decreasing. And what does the induced current try to do? it tries to go against what you're trying to do. So much confidence. So therefore, it should point exactly in the same direction as before. So what's happening? Let's try this. What's happening to the magnetic flux? It's decreasing. What will the induced current try to do? Produce a magnetic field which will try to maintain that magnetic field, which means it should produce a magnetic field which is exactly in the same direction. I tried. That's why the induced EMF produces a flux into the paper, because it was decreasing. It didn't want it to decrease. So it produces exactly in the same direction. All right, the second part, D part, says what is the magnitude of the average induced EMF? Well, is d phi b by dt, just taking the magnitude. That's b dA by dt, because magnetic field strength is constant. So 0.75 times pi multiplied by 0.1, look at that, 0.1 minus 0.03. 20 by 2, right? So diameter changed in the meter. Divided by 0.5, because that took place in 0.5 seconds, and the answer is 0.04288 volt. So here it is, B is constant, it's the area that changed divided by the time. I'm trying to cut down on the time spent in calculation by doing this beforehand, and that's a lot of time actually. Did you notice that the induced voltages are not that big? It's like 0.03, 0.02. It's really small. And the C part, anybody should be able to do. If you got the induced EMF and you have the resistance, how do you find the induced current? Just Ohm's law. By Ohm's law, current is voltage divided by resistance. Right? So I is E divided by R. So 0.04288 divided by the resistance, which is 2.5, and you get that as 0.017 ampere. 8.8 T minus 0.51 T cubed times 10 to the negative 2. You take the negative off n times the derivative of that with respect to time.
Is that big E?
Yeah, big E or small e. Sometimes we use. Yeah, I didn't want to write that, so I just put. Okay. So negative 75 times, when you differentiate, you know that the first one is just 8.8, isn't it? Negative, you're going to get, 3 times 0.51 T squared, of course. That's what I did, times 10 to the negative 2. And then you got to multiply each one with 75, don't forget that, and also with this. Okay? So it's actually 0.75. If you just multiply each number with 0.75, you get that. 0.75 times that, 0.75 that. Fine? So you get negative 6.6 plus 1.147 T squared. And then at T is equal to 1, just substitute T as 1 here, you get the answer. If you put T as 4, you get another answer. Problem done. All right, the car must be moving.
It doesn't matter in 45 because they're the same.
Yeah, because it's 45. But what if it was another angle? If it was another angle, the car must be moving east or west at 90 degrees to BH. BH, I mean the horizontal component. Cos 45 times 0.75, because that was in centimeters, change into meter, times 30, and you get the answer.
Sometimes the easiest questions are confusing.
8 times 10 to the negative 4 millivolt is what you get. And I tried to draw this, B and BH, and that tried to tell you that this is what is cutting through, right? Which is cos. It's not always going to be 45. Right?
Why is it millivolts?
Yeah, because maybe I made it. Is it volt that you get? Yeah. So I just wanted to write it as, let me correct that. So I just wanted to write it as 0.8 millivolt. Is that right? So it's not milliwatt here. Isn't there a better way of doing it? Yeah, there is. Watt.
Is that BH at the bottom?
BH. Number 5. Is E naught sine omega t? It's talking about E naught. And E naught is NBA omega. Looking for omega. So make omega the subject. E naught by NBA. And plug in the numbers. E naught is 120. And 480 is the number. 0.22. What's that? That's the strength of the magnetic field. 0.55 and 0.22 squared is the area. With all that, you get 9.39 radians per second. Isn't that what you said? And then can you find the frequency of rotation? Frequency of rotation is how many times it rotates in 1 second, right? From that, can you get to the frequency? We did that in waves many times. What's the relation? Omega is 2 pi f.
Yeah.
So you just divide that by 2 pi. Yeah, because omega is 2 pi times the frequency. Because one rotation is equal to 2 pi. That's why, one rotation. So f rotations would be equal to 2 pi f. So divide that by 2 pi and you would get it as 1.49 rotations per second. Tau, isn't that the symbol for time constant? Tau is R by L, is the time constant of the LR circuit. And that is the decay. The decay looks like that, and here you have 0.379 isn't it? Decay, exponential decay, time constant is L by R.